Hello and welcome back, and this is the Chipmaster. Right, in this class we're going to talk about the notebook charging circuit. Right, the notebook charging circuit can be a very complex circuit to understand, just like the CPU power supply. Right, this charging circuit is takes some experience and practice on how to understand the methodology and the steps of how to check the charging circuit. So I have a diagram here which I have created, right, and this is a demo video. As I said before, if you want full videos you have to pay. Okay, so this is the notebook charging circuit, as you can see. All right, and here you have the adapter, and we have the battery down here. This is the battery and this is the adapter. This is your current sensing resistors, one for the battery and one for the charger. Right, this is for the adapter, this is for the battery. All right, so here I have some steps, as you can see. Right, and I'm going to explain the steps so that help with the and then I'm going to go over to the schematic here, where I have the schematic, right, of this board. Right, and we're going to go through it step by step. All right, and this is the NL8 Quanta NL8. Right, and this is from the Linux Point HM87, all right, PCH Intel Series 8 platform, as you can see. Right, NL8. So this is the diagram that I have designed, as I said before. So first, when you plug in the adapter, right, it goes through your current sensing. This is your current detection, or we call it the current sensing resistors. Right, so the first step is that the EC must detect the adapter. Right, it must detect the presence of the charger. Right, and this is a signal that is released from the charging IC, as you can see. Right, this is a signal that is released from the charging IC, and this is known as your AC in signal. Right, this is your AC in signal. In some boards this signal will be high, in some boards the signal will be low, depending on the manufacturer of the board. Right, and the EC in conjunction, because this is going directly to the EC. Right, so the next step is that the EC recognizes the battery and read its parameters. So these parameters are like the battery temperature, the charge of the cells of each cell of the battery, the brand of the battery, and certain data information about the battery. Right, the third step is that after the battery is being detected, right, and the parameters are passed through the SM bus. This is your SM bus. Right, this is the SM bus. So let me label it. This is your SM bus. All right, this is your SM bus, right, which stands for System Management Bus. All right, let me bold it a bit. All right, so this is your SM bus, right, and this is your clock and data. So you have one SM bus consists of two lines, or two wires, right, which is a bidirectional communication between two objects. Right, so this, in this case, is between the battery and the IO controller, or the EC. Right, so this is your SM bus to read the battery information. How many charges it in it, the temperature, right, the brand of the battery, the information of each cells, how many capacity of the battery is there. All right, so after this is complete, then the third step is that the EC will send charging instructions to charge the battery. So nowadays you have newer notebooks where the charging IC are completely SM bus charged. Right, these charging IC are completely SM bus. Right, so the EC manages the charging. Right, the EC manages the charging of the battery, and this charging instruction is sent from the EC to the charging IC. So once this EC gets the presence of the adapter, it detects the battery, then it will send the charging instruction. Then the charging chip will drive these two MOSFETs. You have an upper and a lower FET. Alright, upper and lower MOSFETs, these are N-channel MOSFETs, right? So, and this is a pulse width modulation, or PWM. Right, in my class of PWM I will explain the whole characteristics of a pulse width modulation circuit, right, and how it works, and the feedback at front end and back end inductance. Right, so once the charging IC gets the charging instruction, it will drive upper and lower MOSFET, and then it will now charge the battery. Right, so in a typical laptop motherboard, you need roughly 5,000 milliamps to charge your battery. Right, you need 5,000 milliamps to charge your battery. Right, you need 5,000 milliamps to charge your battery. So after the charging instruction is sent and these two upper MOSFETs are conducted, then it will start charge the battery. At the same time, the charge current is detected, right? The charge current is being detected through these two wires, right, as you can see, right? So these two wires are detecting the charge of your battery. So the charge current is detected and sent to the charging chip, as you can see. So this must monitor the charging current, because you don't want to burn your battery, you don't want to burn your adapter. So it must find a way to sense the amount of current, to detect the amount of current that's charging your battery. So if there's an overcurrent situation that's happening on this circuit, then this line, as you can see, this charging IC will output a signal which is a I out, right? On most pins it started I, because I stands for current in electronics. So when this signal releases from the charging IC, it is going to the EC to tell the charging IC the total amount of current that is being generated at this section, and it is being calculated internally inside of the charging IC and is outputted to the EC. So the fifth step is that the EC detects the total amount of charge current from the system. So when this signal, this is your system power supply, which is known as the 19-volt rail, right? For the Mac we call it PP bus G3 hot. So if this is okay, the charge current is okay, then the battery will charge, right? So let's say if this current on this side is about 3 ampere, so let's say the current on this side is about 3 ampere, right? And the current on this side is about 2.5 ampere, right? And the current on the charging section in the current that is charging the battery is about 1.5 ampere, right? 1.5 ampere, right? Will the battery charge? Yes, the battery will charge, because this is satisfied, and this is output into the system to power the total system power, right? If at any given time this current increases above 2.5 ampere or more, then it is being reported to this section. This is their detection for the adapter. This is detecting the total amount of power that is being generated from the system, and it is outputted to the IO controller, and the IO controller will then stop the charging, and you will get plugged in not charging, because you have over current protection. This is known as over current protection, because you don't want to burn up your adapter, nor you don't want to burn your battery. So you must find a way to monitor your current at all times. So this is your feedback section, right? In a pulse modulation class, in my PWM class, I will explain the total and the full concept and everything you need to know about PWM and the feedback circuit. Okay, so this is the steps and how the laptop battery will charge, right? And I will go through the steps, and then I'll show you on the schematic now. Let's go over to the schematic. I have there a diagram here, right? So here's the diagram, right? And this is the NL8 schematic, right? Alright, and this one is the Linux point, which is the Intel Series 8, as I said before, right? So I am going to go to the charging section. Let's say 42, I'm not sure. Alright, so let's find the charging page. Right, so this is a demo class, as I said before, right? I will not explain the entire process, and the practical is accompanied with this course also, right? I will give practical on how to check the complete charging circuit. Alright, so this is your adapter connector CN17, and this is your DC jack, right? These are your filter coils. Remember I said that these coils in the last class, that these are your EMI coils, because as I said before, you have other devices that are giving off a certain amount of frequency when you're using your notebook, right? And this is from like your television, your cell phone, your radio, etc. And these always tend to interfere with the power supply of the adapter. So these coils with this Zener diode, as you can see, is used to protect. So this is a protection and isolation circuit, right? So this is your protection and isolation circuit, as you can see, right? So this is a PL10, PL8, PL9, and this MOSFET PQ39, and another diode of PD10, and another MOSFET here PQ40. These are all responsible for the protection and isolation, because when the EMI comes in, as you can see, here are some capacitors, right? You must have your filter capacitors, right? And your filter coils, sorry, decoupling capacitors and filter coils. So these, as I said, passes low frequency and blocks high frequency, and this one passes high, these caps passes high frequency and blocks low frequency of emission of frequency. Right? I wonder if you understand what I'm trying to say right here. So this is the reason why they've put these coils here, in order to protect the isolation and protection circuit. So this is the process of how they develop the board to protect you from EMI, right? And EMI stands for, as I said before, electromagnetic interference, right? EMI stands for electromagnetic interference. Alright, so as you can see, when you plug in the adapter, this is the DC jack, right? This is your coil. Then after coming through PL10, PL8 and PL9, it produces VA, right? It produces VA, and VA is produced, right? This is the characteristics of quanta. So this is the quanta board. So you must know the timing for each board, and I'll have the timing in the classes for every board. So if you want to learn everything about a Compal board, or a Wistron, or a Quanta, or a Pegatron, or a Dell, or Apple ODM, right? I have all those timing for you, right? You can email me and tell me, and you send payment through my PayPal account. If you want to learn individually, I can send you information, right, directly, personally, through Skype or so, and I will teach you any board that you want to learn. All right, so this is the car, this is a MOSFET. Now after coming through here, it is coming through this MOSFET of PQ39, right? PQ39, as you can see, is a PNP MOSFET, right? As you can see, the arrow is pointing outward from the gate. So this is a PNP MOSFET, and this is going from drain to source. So as you can see, there is a body diode that's inside. Here's the diode. So when this 19 volt come through, it will come through this body diode and exit through the source. So no matter what voltage the gate is on this MOSFET, it will just flow the 18 volt, right? Remember, this is every silicon diode. There's a diode that's inside of this MOSFET, and this is the diode that is draining the 18 volts from here, and it is coming through this diode, and this is going to be 18 point roughly 6 to 18.4 volt. Why? If this is 19 volt, right, this is 19 volt, as you can see, this is 19 volt. So every diode, each silicon diode has a 0.7 voltage drop, right? Every diode has a 0.7 voltage drop. So subtract 0.7 from this, and you will get the answer of 18.6 volt, right? So this is the process of calculating through a Zener diode, right? So each diode has a voltage drop of 0.7 volt, right? And you just subtract your original adapter voltage, right, from 0.7, and you'll get your output, right? So this is about 18.6 to 18.3 volt, right? So doing the calculation, you should get roughly 18.3 volt or 18.4 volt, right? Okay, so after coming through this MOSFET, right, this is a PNP MOSFET, right? It's coming through a Zener diode, as you can see. This is a diode, right? And this is after coming through the diode, it is producing plus VAD. Now after coming to plus VAD, this is your PQ, this is your another MOSFET. This is a NPN MOSFET, as you can see the arrow is pointing to the gate, and this is your N channel MOSFET, right? Will this so in order for this MOSFET to conduct, the voltage at the base or the gate should be what, equal to or greater than the voltage at the source, as you can see, and then it will drain. If you know the notice direction of the diode is now reversed, right? So you need to get a high voltage at this gate in order to produce the conduction, so we can produce power SRC, right? So in order for this to produce, what will happen? Now if you notice, there's another transistor here. This has 6 legs. It's PQ14, right? And you can see it has 2 transistors inside. These are transistors. These are MOSFET. These are transistors. As you can see, plus VAD. See, plus VAD is now passing through this MOSFET. This is the base. This is the what? The emitter, and this is the collector. So plus VAD coming to the 4th pin. This is the 5th pin. This is 2 MOSFET. See, Q1, Q2. Let me zoom. Right, so Q1, Q2, so Q2 plus VAD is coming to the source. This is the emitter, this is the collector, this is the base, right? When it comes to this MOSFET, this transistor, as you can see, right, this voltage is going to flow and conduct and come through, and this gate is going to be pulled up, as you can see, right. This gate is going to pull up, and this is 18 volts coming here, 18.4 volts, right. So then therefore our MOSFET here will be cut off, right. So in adapter mode, so it is cut off because the voltage here is 18 volt, 18.4 volts. So the voltage at the gate is the same as the voltage here. This is flowing from drain to source. So this will cut off if high voltage come to this point. But because this has a body diode that's inside, it will always flow in this 18 volts. Right? It will flow in the volt coming through the diode to drop it to 18.4 or 18.3 volt. Right? Now this MOSFET, as you can see, this is a MOSFET twin one. As you can see, it has another one plus VA is coming to here. As you can see, this is plus VA. See, plus VA is coming at the next through the base of this transistor. So the base of this transistor is conducting, 18 volt will flow here, right? And what will happen? These are creating a voltage divider. This is creating a voltage divider. So this is a 1 mega ohm resistance. This is a 1 mega ohm resistance, and it's connected to ground, as you can see. So it will pull this to about 7 volts. Right? It will conduct. Right? As you can see, the conduction is coming through this 2 kilo ohm resistor. This is the collector. This is the emitter. This is the base. This is the collector. Alright, this is the emitter, and this is your base. Right, B, and this is your C, which is collector. Right, this is your base. Right, this is your emitter, and this is the collector. Right, so it is conduction. So when this 19 volts come into here, right, 19 volts come into here, it will come to the base of Q1. Q1 will what? Will conduct, right, and it will go through this resistor, a voltage divider, to pull down this 19 volt to 7 volt, right, and then your MOSFET will conduct because it's a p-channel MOSFET, so the voltage at the gate must be less than the voltage at its source, and it will conduct through, coming through this pull down resistance. Alright, so this will conduct, right, and then this MOSFET, as you can see, is being controlled, as you see, bat discharge underscore gate is coming through this IC. This is your charging IC PU8, which is a BQ24738H. As you can see, this is BQ24738 IC, and this is your charging IC, completely SM bus charging IC, as you can see. So this is the new models of charging IC that are now on most notebooks, right? And you should understand the working conditions of this charging IC. All right, so in order for this MOSFET to conduct, what will happen? We need some working conditions, right? Can anybody tell me the working conditions of this IC in order to produce AC drive? Alright, here it is. So first you should check the supply, VCC. So VCC is coming through a delay, as you can see, right? This is a delay. So this is a 22 kilo ohm resistor, and this is a 0.47 kilo ohm resistor, right, as you can see. So at the same time, as you can see, this is 19 volt is coming, right, to pin number 20 of this IC, and plus VAD is coming from here. Sorry, it's coming from here. This is 18 volts. Sorry, after they coming through the diode, this is 18.6 volts. Right, this is 18.6 volts coming, right, to charge PC 187, and it's coming to pin number 1, pin number 20. Right, at the same time, adapter detection signal plus VA, see, plus VA is coming from here. So this 19 volt is coming through this voltage divider, right? And it's coming, this one is 430 kilo ohm, and this one is 69.8 kilo ohm, and it is conducting, and it's coming to pin number 6. So this is about 3.1 volt after conduction, right? If you have your voltage divider calculator, you can calculate. This is 18.6 volt, right? So the resistor of resistor 1 is divided by resistor 2, right, over R1. So this is the formula. You should know your formula, but you have calculators which can calculate this voltage for you, and this is coming through a pull on resistance to 3.1 volt, right? So the characteristics of this strip is that the data sheet is that this has a pin that is on the voltage lockout. So it's ULVO, right, on the voltage lockout protection. this is about this is 3 volt, right? And the minimum, this is the minimum threshold of 2.4 volt coming to this pin. So if you read the data sheet, let me see if I can find the data sheet. Alright, so this is the data sheet. As you can see, BQ247880 is the same, right? It's the same, and it's a notebook ultra detectable tablet PC, industrial medical equipment, alright, industrial innovative charge control with hybrid power and boost mode. Alright, so we're going to go to the pin definitions of this charging IC. Alright, so the pin definition is very important when you are troubleshooting. So let's look for VCC. Alright, VCC is an input power supply from adapter. Alright, input power supply from adapter or battery. Use a 10 kilo ohm resistor along with a 1 microfarad capacitor to ground to what? To a low pass filter limit rush current. In order to control the amount of rushing voltage, it is best to connect a resistor to delay. You need to delay this because what? You want a low pass filter to the limit the inrush current, or a diode is connected to VCC. It powers the charger IC from input adapter and battery. So in order to get this signal to come in at a certain time, it is best to put it through a delay circuit, as you can see, right? So here's the delay circuit. So PR94, PR194, and PR and PC178. So as you can see before, as I said, the resistance is multiplied by the capacitance. So R multiply by C. So if this is 22 kilo ohm, so 22 kilo ohm multiplied by 0.47. Right? Can anybody tell me the answer for this delay? Alright, so it's 22, right, multiplied by 0.47, and that's 10 milliseconds. So it will take 10 milliseconds for it to come to power VCC. As you can see, 10 milliseconds, because this is calculated in milliseconds, right? Let's go for the detection pin now. These two pins are connected together, as you can see, internally. So let's go to the data sheet. Alright, so this is the data sheet I have. Alright, so the next one we have AC detect. So we're going to look for AC detect, and let's find that pin definition. Alright, AC detect. Okay, it's right, it should be here. Oh, here's it. So AC detect, adapter detection input, program adapter valid input threshold by connecting a resistor divider, so from adapter input to ground. When AC detect is above 0.6 volts and VCC, which is the under voltage lockout protection, and RGEN LDO, this is your low dropout volt of 6 volt, is present, AC okay, the comparator input current, right, discharge current, independent comparator, and the power monitor, right, which is enabled with the SM bus. AC detect is about 2.4 volt, and VCC is above SRN and below ACVOK, and ACOK goes high, then it will output RGEN. So this is your low dropout. Here is it, RGEN. So when this condition is met, VCC and AC detect is conditions are met, then it will output a linear voltage. This is a linear voltage of 6 volts coming, and it is now named as RGN6V. So this is 6 volts coming out of this IC, right, and this is your linear, right, and this is also helping to create the V boot. This is your V boot upper MOSFET. This is your driving linear voltage of the V boot. So this is also helping to drive the upper MOSFET. As you can see, here it is, RGN6V coming through a diode to boost, and it is connected to drive the upper MOSFET. This is known as the V boot, right? This is a demo video. I'm going to stop here. If you want full videos, you have to pay. If you want to contact me personally, you should send payment to my PayPal, and I will teach you live on Skype, right, and I will give you complete working conditions of how to solve battery charging problems. All right, so thanks for watching.